Okay, so when on Monday morning I was asked to bring together this talk for today with no slides, I thought, shit, what do I do? So I reached out to Genevieve Dunton, Scott Duncan, Tom Baranowski, Stuart Trost, Jordan Carlson, who all provided me with slides today, because really I focus on older adults, as you'll see tomorrow, partly because it's so difficult to keep up with the literature in all these populations. The youth are an entirely different area, and so I haven't been able to keep up, although I have done work with Jason, and that's why he partly said maybe I could represent. And thanks to Rick, because we just were sitting at dinner talking, and I think sometimes we're so focused on what we're doing, we forget to stand back. So having a conversation with him last night allowed me to stand back again from what we're doing in our research, and I think I've been able to incorporate that into this presentation. And funding from NIH, the American Heart Association, and UCSD internal projects too. So when I think about physical activity in youth, I think about settings. That's the first thing I do. So I think about places like schools, active transportations, sports, and then the home. So these are places where we can do physical activity. So I think that's different to other populations, that there aren't necessarily, some of these would be the same for adults and older adults, but for example, the school is a unique setting. That's one way when I think about how's the technology relevant, I think about how is it relevant in these different settings, or how does it help us learn about these different settings? Because if we're to intervene in young people, we have to know when and where to intervene. And so if the technology can help us do that, I think that's a great benefit. So the first slide, and this comes from Scott Duncan and Jasper and Stuart down in, Tom down in New Zealand. So this is examples of when you have GPS data collected and accelerometer data, and then you can map them and see where the physical activity is occurring in these different locations. So then someone like Jordan Carlson, for example, has then been able to say, okay, what % of the day is spent being physically active in these different domains? And again, that gives us opportunities to say where can we increase that time, but then what are the environmental factors that one would have to address to increase that time. So the other piece that Jordan's also been working on is thinking about settings. So basically we're saying, okay, if we have to understand physical activity in these places, how can we analyze physical activity in these places? Because it's not that we're necessarily going to have an accelerometer or a Fitbit on every person in every location. So are there things in the environment themselves that exist that allow us to analyze physical activity in specific locations? So he has an R21 related to this, where essentially there are cameras in many places. So then what his R21 is doing, so there we go, is taking images in these locations and then training, using machine learning to actually then train to be able to do the image recognition, but recognize people and recognize movement. So his sort of ground truth is these kids in these images are wearing accelerometers, so he knows how active they're being, and the question is, can the analysis of the video also match that intensity of activity? So can we define activity intensities from these environment-based remote images? So he's just started that, and all sorts of challenges. So for example, I know we were talking about this basketball image, and sometimes the kids are sitting out, so they're not in the image, so you need to know which accelerometer is sitting down and out. And so they needed to have the number actually up here instead of here so they could identify participants. So there's all sorts of logistic things like that you don't really think about, and they all sort of make our lives more difficult. I also then wanted to represent Genevieve Dunton's work, where basically she does ecological momentary assessment, and from doing that she's really able to learn a lot about the parent and child. And again, we have to think when we're intervening with kids that we need to understand both. So where is it that they're doing sitting time together? Where are they doing physical activity together? And you can actually see here, for example, there's a lot more joint sitting time together. So if we think about developing interventions, clearly working with the parent is really important in that situation. Maybe not the case for physical activity. So this type of information can really help inform that. And again, she's also able to assess where people are and so matching not only just the activity, the location, but are you with your parent or not. And other things that have come from being able to do this ecological momentary assessment is essentially you can also ask about people's intentions, and these graphs just show the relationship between people's intentions and whether they actually then go on and move and become physically active. So again, I think when we're hearing about our theoretical models this morning, we can really start to understand, intention isn't just this thing that exists and never changes. It changes a lot temporarily, and sometimes we act upon it and sometimes we don't. So again, I think we're going to be able to improve our theoretical models by having this better understanding. And going forward, she has a study, the MATCH study, where she's collecting 24-hour recalls and cortisol data as well, so looking at how stress is related to different activities. So now I'm going to talk a little bit about the work that Jay and I have been doing together. So essentially he was doing a bicycle train intervention, a pilot intervention, and wanted to know that he was going to be able to measure cycling in these kids. So as you can see from the image, when they're doing the bike train, so that's basically when kids organize and bike to school together, that there will always be somebody from the program with them. So they kind of are the observer, the ground truth of knowing, did the biking occur? So that's much more, do kids turn up to a bike train and then bike to school? What he also wanted to know was, are they also cycling at other times when they're not in the bike train? And is total moderate vigorous physical activity affected as well? Not, or do we have this compensation where, you're doing the bike train, so you're not going to be active at other times of the day? Because we certainly see that in older adults. We get them to be physically active and they need to take a rest after that. So let me just give you a little bit of the perspective of the reviewers. So as someone who had been working on GPS and accelerometer data, we had developed the PALM system, which aggregates accelerometer and GPS data and then identifies different transportation modes from the GPS data. So we had already had that system running and certainly had done a lot of validation of it in adults. So that's what we proposed to use in this, for them to use in this intervention in the first round. And the reviewers basically said, you can't measure cycling from a GPS. And so I was like, okay. And they said, you have to have an accelerometer on their ankle. Because of course, the only way we can measure cycling is if you actually get this movement. I said, bullshit, because essentially I had studies where I had used machine learning techniques to recognize cycling from the wrist, from the hip, with or without a GPS. But I said, okay, let's not argue with that reviewer. Say we'll add an ankle accelerometer, because that's the thing I think we really have to understand in sort of the physical activity field, at least, is we don't have to measure the physiological movement, but the pattern that comes from the signal is what we're analyzing. We're not actually analyzing, does the ankle move? But when you're on a bike and the accelerometer on your waist is shaking around in a very different way than when I walk or do anything else, that's what tells us it's bicycling. I don't have to have it on the ankle to do that. So as you can see here, whether it's at the waist or the ankle, here you can see that there are very different patterns. Now, obviously, on the ankle, some of those patterns seem to be stronger than on the waist, but the difference between them is what we're trying to identify, because I want to know, can I identify sitting from walking? Can I identify cycling from jogging? And we always keep our riding in the car separate. Yes, that is sitting, but it looks, as you can see, it looks very different in the car than it does in sitting. So we don't want to misclassify and sort of confuse the algorithm by giving it a case of sitting that doesn't really look like other types of sitting. So here's what it looks like when you do the traditional cut points that we've used for accelerometer data. You can see that the cycling really always falls under the cut point. So that's why basically people have said you can't use an accelerometer worn on the hip to measure cycling. So it's not the device that's the problem, it's the cut point. It's using a threshold like this is the problem. So let's make sure we're not throwing the baby out with the bathwater when we say this device can't do it. No, the way you analyze the data might affect whether you can do it or not. So as you can see, that's why the thresholds wouldn't work for something like cycling. So essentially what we had learned from our machine learning work that we had been doing in adults is, obviously when you do the machine learning approach, you have to train it. So you have to have some training sample where you know what the people are doing. And we had collected data on adults at this stage, and I'll tell you about that next, but in kids, so what we had done in adults is we'd started with protocolized studies where we'd gone out and said, do this, do that. But it's not free living. So then we moved to our SenseChem work where we had images and we had free living. Now we hadn't done that yet in the kids, and we didn't want to start for this R21 to do that in the kids. So we said to him, okay, let's do a protocolized system to start with training. So basically we got the kids, 30 kids, had to do specific activities. So it had to be the ones we were interested in: sitting, walking, jogging, cycling, riding in a car, because those were the things that we wanted to analyze. So then basically you can see the different devices, and this is the accuracy here. So because it's protocolized data, it's very clean data. That's why we can get these ridiculous performances, is because you've only got a few things you're trying to predict, which also helps. It's very clean data. So we already knew from our previous work, because we had done studies where we had trained on a protocolized data set, then applied it to a free living data set, and we could see that you would lose performance. So we knew that even if we applied these to his study, that the performance wouldn't be this good. But essentially it showed us that, you know, we can train this on this data. And for us, the biggest thing here was that it didn't matter so much where the device was or where you wore it. So because the waist was still the best location for total physical activity data, we went with the waist and GPS. So that's what he threw out the ankle, because that silly reviewer didn't know what they were talking about anyway. So to go to the adults. So we were saying, okay, we've developed this machine learning on the protocolized data set in the kids. But we know from that what happens is when you apply it to free living, you lose some of that accuracy. And part of it is when we do our free living work, we do our classifier, and then we apply this hidden Markov modeling that smooths the data. So the chances of you walking for 5 minutes, cycling for 1 minute, and then walking for another 5 minutes, the probability is not very high. So what you get is this smoothing based on the probability. Now when you have this protocolized training sample, you have no probabilities for what happens in real life. So we knew that was important. So what we said is, okay, how did that kid algorithm we developed on the protocol apply to our adults that we did have free living data on? And it actually worked pretty well. Definitely for like walking, you lose a lot. But for these behaviors, what the sort of signal coming from the devices looks similar in the kids as it did in the adults. So then what we basically did is combine our two data sets, the free living adults and the kids, so that we could then use those probabilities from the adult sample. And that's essentially what Jay then used on his intervention trial. But what was interesting and what was great is when we applied that machine learning back to his intervention trial, we had, remember, the people that were cycling with the kids, they could confirm our algorithm was detecting that cycling too, so it was sort of further validation. But then what we did get was this situation where when kids were playing in place, that was also classified as cycling, because you've got to understand these algorithms are trying to make a decision between 5 behaviors, which shall I classify? And kids playing in place in the playground looked more like cycling than any of the other behaviors. So after that, we sort of added an additional layer of, and if there's no distance of a certain threshold, then it's not cycling, it would be in place. And you sort of think, how can that happen? Why is the GPS? But when someone's in a playground right next to the school, we saw so much GPS error that it ends up looking like they're making progress. So we had to get beyond that threshold to do it. So even, and that was what was, a good learning point, is we knew the things we were trying to predict, but we didn't think about the things that the kids were doing that we weren't trying to predict that would interfere with our ability to classify behaviors. So I think that's what's really important, is focus on what you're trying to do, but then if you don't think about other things that may be not of interest to you but actually occurring in the population. So we have a study where we then did actually collect SenseCam data in kids as well, so again, we can refine these algorithms with that data. In some situations, we had matched parent pairs because we were really interested in that. Do kids and adults, when they're doing the same behavior at the same time, do they look different on, not physiologically, but do they look different on the devices? But I was really interested to hear that Mingay had done his e-button in schools, because we didn't even go there with our SenseCam, because it was like we'd have to get ethical approval from the schools. I've worked in schools a lot, so I'm going to follow up to see what he did. So we didn't have the images from the kids in the schools, and they're definitely going to be a lot harder to annotate. I had my son wear the SenseCam, and when he's lying down watching TV, the camera's looking out the window and he's looking at the TV here, and he never sits still, and he couldn't stop touching the thing. And so you can see that there's going to be so many more challenges. And certainly for us, we basically, the more data we have collected with our SenseCam, we broke the browser that was developed. So again, this browser was developed to annotate SenseCam data, but not at scale that we're working at. So we've had to develop a more sophisticated browser that also has more of this image recognition built into it. So it's sort of that expert automatic match that Kara was talking about. So also Stuart Trost has been doing work in this area, and so he's done more the protocolized settings, because what he's interested in is energy expenditure. So that's kind of one of the differences. We can do the free living behaviors because it wasn't so important what the METs of the cycling was for Jay. He basically took the METs from the compendium and applied that to the cycling that we identified. Because again, if we're going to convince transportation planners to change the built environment, they don't care about energy expenditure. They just want to know you're cycling in the bike path that they built. So different perspectives in our field. And so what this shows from Stuart's work is what he's looking for is any bias. And he basically first developed a neural network, and you can see that it's performing better than some typical cut points, and this was in kids. And then he's also done some work in the preschool children as well. So here you can see he's got the neural network, he's got a randomized forest and the support vector machine. So between the random forest and the support vector, they're kind of working similarly, but he saw that if he changed some of the time frames that he got better performance. And again, just to sort of, he's also been working on hip and wrist together, and seeing that combination of the hip and wrist is probably the best one, and again, how that performs compared to the cut points that are out there. So we're definitely making improvements through these new techniques. Switching to sedentary behavior. So essentially the active PAL is a device that can be worn on the thigh, and it estimates posture. Your actigraph is worn on the hip, and essentially if you're using the existing cut points on the actigraph accelerometer, it's based on intensity, so it's not a postural measurement. But many studies have said when you go over that 100 threshold in the actigraph, that means you're breaking up your sitting. And it's just not the case. It means that you're moving. And so even though, for example, the active PAL that has definitely some good observational validation, they have similar predictions of the percent of day that you're sitting. But as soon as you start to break it up and say how many times do you actually transition from sitting to standing, the actigraph totally overestimates that and then underestimates the amount of time you spend in prolonged bouts, for example. So as we start to say, how do we bring data together, or the patterns of how we move and how is that related to our health, it's really important that we're having an accurate measure to do that. Maybe not for the total day, but as soon as you want to start to make more sophisticated metrics of breaking up sitting time, then it's not sufficient to have the cut point on the hip. And one thing I just wanted to point out here is some of the correlations between them as well. So for example, even though we see there were only 68 sit-to-stand transitions in the day, and this had 307, the correlation between them is quite high. So I really caution people who are doing studies saying, the Fitbit is correlated with the actigraph. To me, that's just still nonsense. You need to have a ground truth to know what is the difference in the behaviors. So then finally going to the group in New Zealand, they're also doing some work with the activity. They're putting it on the back and the thigh, and one of the things there, it's got a temperature sensor, so they're finding that's very helpful to indicate to them when the kids take it off or not. So again, that's been a problem that we've had in our field. We've been having to say, when are people not wearing the device? So just a quick look in the literature. There was definitely some studies out there in adolescents and children looking at different types of Fitbits and sleep. And again, I think as we think about physical activity and then now sedentary behavior, we also now have to think about sleep, so it's important. And so what I saw here was that with the Fitbit Charge HR, they were saying that had been validated for sleep in adolescents, but the Fitbit Ultra was not. So I think as the devices improve over time, they can be validated. And at first, when I was reading the two studies, I was thinking, how can one group say it's valid and another group didn't? And they were sort of saying the group that said it wasn't valid said it because it wasn't valid for clinical sleep measures. But I think partly it was also because of the devices. And this is an example where somebody compared the Fitbit Zip to the actigraph in adolescents and just did correlations. So I really don't know what that means. So just to finish up on the interventions, what's in the literature out there? There was a review of 5 studies that used various wearables devices. So these were 5 small randomized controlled trials. In addition to that, there was a pilot of the Fitbit and Facebook and the Fitbit at recess. So I think it's coming out there. I know there's a lot of studies going on, but they're not necessarily yet published, and the ones that are still quite small. Again, there was a review of 9 mobile phone app studies, mixed findings. One of them was that perhaps having a peer component in it was helpful. I think the other area we have to think of, and thanks to Tom for this, he sent me about 60 slides and I had to make it into one. So that's where I feel like, how can I stand up here and represent a whole field with one slide? I think that's the thing. There's so much complexity in each of the things. To get the right exagame involves as much as you trying to get, analyze the food data. Each of these areas is their own specialty. And so essentially here, if it's actually played, then you can get increased energy expenditure. Some studies show impact, some don't. Some show impact on BMI. And again, some kids in some places are using exagames and it's working. So I think that's what we always know with public health. It works for some people some of the time. So that would be my caution to this. Technology isn't going to solve it all for all people. It will work for some people in some situations. And us finding out who that is is important, but it's not a silver bullet for public health. And the parents might be key in starting in siblings. And then that got me thinking about other mobile games, because again, back to the GPS. And so then in October, they just published this study with Pokemon Go as well. So then the folks who actually did the Pokemon Go and actually then collected experiences definitely had an increase in their steps, and it went up to similar levels to people who were using wearables and apps in this study. So this was a great, interesting time series analysis. So I think that's important when we intervene with kids to think about things like this. The question for always is, how long can that last? But again, that's what was said this morning, is that we can find that out. And then we always, like if you think about advertising, they've known it for years, that the campaigns change because they lose their impact. You have to always renew. So just to end on the key discussion points from my perspective on the physical activity for kids. Fun is a key element that technology can deliver in all places. I think that's so important. And the role of both children and parents in using the technology is really important. Again, I really hesitate to just have correlations with other devices. We need ground truth validation, and getting this in kids is more challenging than other groups. Again, if we can do validation and free living of algorithms, I think that's important. But one of the things I've learned as well is this, I have computer science colleagues who can publish an algorithm and say, yeah, I've solved the problem of recognizing this or that. But then when I take it and try and actually use it in a study, there's not very generalizable. So again, let's not be fooled by people saying that they've solved the problem. The chances are they haven't. Again, what's the difference if we're looking at behaviors versus energy expenditure? And in fact, can we combine these data sets like we did in Jay's study, where we've got some protocolized data and free living, including things like the active power now that we could use. And there are data sets like a large international study that we can start to apply it to. But again, challenges for us include a scalable annotation system. Is it better and faster than the human recognition? When the devices change, it can really affect us. They changed sense cams partway through our study, sent us new sense cams. They kept resetting to the year 2000 every midnight, the battery life. We sent them back and asked for our old ones back, and we said, so how are you testing these? On our desk, they said. So we said, okay, here's our protocol for how we test every device. So again, working with manufacturers to me continues to be challenging. And I think one of our roles is to really try and change reviewer misconceptions. There was a misconception that you need to measure cycling from the ankle, and there's a misconception that you can automatically recognize foods, right? There's so much talk where people just say it, and it's like, so some things are possible and people don't realize it. Other things are much more challenging and they don't realize that. So I think that's really important, because if we don't have informed reviewers, then it's very challenging for us to continue to get funding. So thank you.